Hi, welcome back to Math 533, Topics in Euclidean Geometry. In the next few videos, we're going to look at parallel lines. Now specifically, we're going to look at parallel lines in Euclidean geometry, and next week we will see another kind of geometry where parallel lines also make sense, but behave very differently from the Euclidean sense. Now the historical background of what we're talking about is a problem that interested mathematicians basically from the time of Euclid until the 19th century when the problem was solved. Depending on exactly how you mean that, it was solved at some different moment in the 19th century. We will briefly touch on the history of it in this video, and then in subsequent videos we will take a look at actual consequences for the geometry. Problem with parallels. A classical problem of great interest to mathematicians was Euclid's fifth postulate. So if you recall, Euclid's 5 axioms, which I've reformulated into a modern language, are the following: that we can connect any 2 points with a unique straight line segment. The second one is a straight line segment can be extended continuously in a straight line. Often this is understood to mean that a straight line should be infinite. A circle can be drawn with any center and any radius. All right angles are equal to one another. But these are all basically one sentence long, or short sentence longs. And now for the fifth postulate we have: if a straight line falling on 2 straight lines makes the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which are the angles less than the 2 right angles. That's a mouthful. So let's have a little sketch here of what that means. So we're saying we have 2 straight lines, L1 and L2. And we have the straight line that's falling on the 2 of them. So that's this line I'm calling T. And so I have the 2 straight lines are L1 and L2, and it's falling on the straight line T. Okay. And we're interested in the angles. So we make the interior angles on the same side less than 2 right angles. So that's where Euclid in his geometry didn't have this notion of degree. So we need to talk about 180 degrees as being 2 right angles. So that means this angle together with that angle. And it's saying that if I continue my 2 lines L1 and L2 until I get an intersection point, it's going to happen on this side over here on the right somewhere. Right, so whereas on the other side, of course, we have our 2 angles on this side. Together they add up to more than 2 right angles, so to more than 180 degrees. And that's not the side that we get the intersection on. Okay, so this is often called the parallel postulate from a work of a Scottish mathematician named Playfair. This turns out to being equivalent to a parallel postulate, which says, given a point P not on the line L, there exists a unique line L prime parallel to L passing through P. So in my picture here, I have my line L. I have my point P. The point P is not on the line L. And there exists a unique line L prime, which I have here in dashed, or I guess dots. Right? This line right here is the one that's guaranteed to pass through P, and that's parallel to the first one. And there are 2 things in this formulation, right? There exists and there's unique. So there exists a unique line L prime passing through P. So a question that was of historical importance was the question of whether the parallel postulate is actually necessary to take as a postulate or not, or is it secretly a theorem that you can prove from the other axioms that we have in Euclidean geometry. So there's a long historical interest in this question. Euclid didn't explicitly say anything along these lines, but if you notice the way the elements is organized, you see that he doesn't use the parallel postulate until proposition 29 of book 1, which means that he delayed it for fairly long into the content of the elements. Then this continued being of interest in late antiquity. Ptolemy in the 2nd century, I guess that's maybe not even late antiquity, and Proclus in the 5th century tried to prove the parallel postulate using other theorems, using the first 4 axioms. Then in medieval times, this was studied a lot by mostly Arab mathematicians. There was Ibn al-Haytham, who was often called Al-Hazan in the West. So he studied it in the 10th century. Omar Khayyam, who's maybe more famous as a poet, you might have heard of the Rubaiyat of Omar Khayyam. He studied this problem. He was a noted mathematician and astronomer in addition to being a poet. Nasir al-Din and Sadr al-Din, who was his son, both addressed this question in their writings. And they were in the 11th and 13th century, respectively. Then some Italians started thinking about this problem in the late 17th century, early 18th century. That's Giordano Vitale and Girolamo Saccheri. And then Johann Lambert did some work in the mid-18th century. And then finally Playfair, that I mentioned already, who reformulated Euclid's axiom into this perhaps simpler looking format of about the existence of parallel lines. Okay, some of these people I've put in bold because the people I've put in bold are important. They made important contributions that got built on in our next slide. So it turns out that this 5th postulate is indeed necessary. We need to impose some statement about parallelism. And this was something that became clear in the 19th century. So roughly at the same time, Lobachevsky and Bolyai developed independently hyperbolic geometry, which is the study of a geometry that has the first 4 axioms of Euclid, but replaces the 5th one with a different axiom, which turns out to be that you ask for there being the negation of the 5th axiom. And that forces you to have infinitely many parallel lines through your point. Okay, when Gauss was told about Bolyai's work, he claimed very convincingly that he'd already studied this question but just hadn't published the work. There are some letters of Gauss in which he explains the ideas or gives some hints of the ideas to his friends and colleagues. And so these 3 mathematicians are considered the inventors of this so-called hyperbolic geometry. Riemann was a later mathematician. He extended this idea significantly. And then the Italian mathematician Eugenio Beltrami, he showed that hyperbolic geometry exists at least as much as Euclidean geometry does, in the sense that if Euclidean geometry is consistent, then hyperbolic geometry is consistent. And then, as we maybe mentioned a couple weeks ago, the consistency of the axioms in Euclidean geometry were then proved by the work of Tarski in the 1920s. Okay, so this answers the question, yes, the 5th postulate of Euclid is necessary in order to develop the theory of Euclidean geometry. Now, the idea, I had those bolded names, and I guess then Lobachevsky and Bolyai. The idea, or one of the important ideas, is the development of something called neutral geometry, where you make as many theorems as you can based only on those first 4 axioms of Euclid. So sometimes this neutral geometry is called absolute geometry, depending on the book or website you look at. And there are many theorems that we've seen so far that are theorems of neutral geometry. Actually, everything we've done so far, in detail at least, has been a theorem of neutral geometry. So, for instance, our angle-side-angle congruence theorem. We did not use parallel lines in that proof, so it is a theorem of neutral geometry. The isosceles triangle theorem, that's an immediate consequence of side-angle-side, so it also does not use parallel lines. The side-side-side congruence, that also holds in the absence of the parallel postulate. Right? We don't need the parallel postulate to prove any of these theorems. Right? Or the one you've done recently or are doing on your homework, the pointwise characterization of the perpendicular bisector. So these are all examples of theorems that are theorems of neutral geometry. So of course, every theorem of neutral geometry is also a theorem of Euclidean geometry. Right? A neutral geometry can be Euclidean, or it can be something else. And there are some theorems you know and love, or hopefully love, that are not true in all models of neutral geometry. They're true in Euclidean, but not in a hyperbolic geometry. So for instance, the sum of the angles in a triangle adds up to 180 degrees. That turns out to be a statement that is equivalent in neutral geometry to the parallel postulate. The Pythagorean theorem is one that holds in Euclidean geometry, but it is not a theorem of neutral geometry. The existence of non-congruent similar triangles is actually a theorem of Euclidean geometry. In hyperbolic geometry, it turns out that if I have 2 congruent triangles, two similar triangles, they are actually congruent. It turns out that a neutral geometry is either Euclidean geometry or it's hyperbolic geometry. This is an important theorem that gives you a dichotomy in the neutral geometry world. This is Lobachevsky, Bolyai, and Gauss show there exists a different model of neutral geometry, the hyperbolic geometry, which is fundamentally different from Euclidean geometry. And Beltrami basically used Euclidean geometry to, in some sense, construct a model of hyperbolic geometry, and that construction shows that if Euclidean geometry makes sense, then so does hyperbolic geometry. And these ideas led to the modern field of what's called differential geometry or Riemannian geometry. And there are many, many mathematicians associated with that, notably Riemann. And so we have this fact that if we imagine some kind of a Venn diagram, right over here I have all neutral geometries, then we have a split in 2. We either have Euclidean or we have hyperbolic. Right? So there's nothing else. It's a given neutral geometry is either a Euclidean geometry or it's a hyperbolic geometry. And then if you have reasonable axioms, essentially all models of Euclidean geometry are equivalent, and essentially all models of hyperbolic geometry are equivalent to each other. Okay, one needs to be a little bit careful about what that means, so we're not really going to dwell on that. Okay, so that's our historical background. Join us on the next video when we talk about consequences of the Euclidean parallel postulate. And remember, we're going to save hyperbolic geometry for a brief introduction next week. The name of the class is Topics in Euclidean Geometry. It's not Topics in Hyperbolic Geometry, so we're going to give pretty short shrift to the hyperbolic geometry. See you on the next one. Happy mathing.